And now that things are actually recording, I'm going to announce again. There's a quiz tomorrow. Posted online is a sample for that quiz and a solution to that quiz. I guess if you found your way to the recording, you know how to find the sample as well. Yeah.
So for the quiz, so is the format just written response, or is it going to be like multiple choice?
Let's take a look at the sample. So there will be some written response. There will be some multiple choice. There will be some very short answer. So hopefully that helps. Okay. Yeah. It will be the only thing we do tomorrow in class. So in general, most people leave by like the 45-minute mark, but that's not saying that you should aim to leave by the 45-minute mark. You have the full 50 minutes. Cool. Let's begin. Yeah.
I can see that a bunch of people have like a packet.
Oh. Gotcha. Okay. So, I think that you have unfortunately started on the first day when I haven't bought a bunch of extra copies of this. So, the way that the class generally runs is there's like a big note packet, and I have people take notes. The note packet is exactly what I lecture out of. And so take notes however you please today. I don't have an extra copy to do right now. Right afterwards, if you want to follow me upstairs, I can give you an extra copy. If you're a mobile device user like a laptop or what's the word, tablet user, the PDF is online. You can pull it up right now if you want. If you're not, then you're not. And if you want to find it, if you search for me and use UEC, you will find my fossil webpage. Yeah.
For the quiz, do you want us to answer it like in the open-ended number, or just solve it?
I want less detail than that, but it's like if you just read the problem and then I see the answer written, and I don't see how you went from A to B, then I probably will be upset. So I want some amount of supporting work. Write it as if you want someone to be able to read it, but don't necessarily go as heavy as you would on the open-ended. Neat. Yeah.
So does that mean like you have to put words at all on it then?
If
You just like write your steps?
If there are any ideas that seem complicated enough that someone looking at it would need words to understand, then maybe add some words. You'll have plenty of time. So if someone should be able to understand what's written. If you think it needs some words, then add some words. Groovy. You had a question. Your hand was up.
Yeah, that one was like.
Oh, that was a question?
Yeah.
Oh,
And
okay.
also it's like for grading, right? So do you do necessarily like curving, or like I just want like for your when it comes to like quizzes and exams, do you do any type of like curving or anything like that? Or?
Not usually.
Okay.
If it becomes clear upon grading that a question I asked was somehow unfair, then I account for that. But no, usually the grades stand as is.
Okay.
Yeah. Groovy. Let's now begin. 6 minutes in. So we talked a little bit about some properties of functions: evenness, oddness, intervals of increase, decrease, rates of change. What I would like to, the last thing in this particular pack that I want to do, which if once you get the PDF pulled up, this is page 25 in there. Okay, cool. Is the idea of maximization, minimization. And I'm going to do this by telling you that you in fact already know how to do this by doing it. So here is the graph of that function. You have some function that looks something like that. What is the maximum output value this function takes? if you like, this is remembering what output value means. Output value of a function is the y value. So asking for the maximum output value is the same as what's the biggest y value you see on this graph, which is
Wouldn't that be positive 5?
positive 5 because of this point. Negative 5, 5. That's the biggest y value you see. All right, so now let's ask a related question. What input value corresponds to that maximum output value? What input value gives you that maximum output? X equals negative 5. So right, those are both things that you already knew. If you have a graph, you can just look at it and see what is the biggest output value this function has. And you can see what is the input that gives you that output. Same question, what is the minimum output value this function has? Yeah?
Negative 4.
Negative 4, perfect, because of this. What is the value that, what is the input value that corresponds to that minimum? X equals 2? Good. So, something that mathematicians will do a lot is they'll add words like locally to a concept. So a thing happens locally if that thing happens when you only notice what happens nearby. And on the old .coms, there was a good bit of trick I could do because it allowed like a zoom in factor of like 20 or 40 fold. So I could zoom in real close on the graph. I can't on this one. But the idea is, suppose that you looked at this graph. There's a point on the graph. Let's suppose that you zoomed in just on that very small window. If you only saw the amount of the graph inside of that box, would you think that that point is a maximum value, gives you a maximum output? No, because you could like look really close and there's a bigger output. So this is not a local maximum. So even when you zoom in, it doesn't look like a max. Is there any point on this graph where if you drew a very small box around that point on the graph, you would say this looks like it should be a maximum value? Yeah.
The tip of like the W, like another part.
Yeah, max. So this point?
Yeah.
Yeah, if you only saw that much of the graph, then you would sure think that looks like a maximum value. So I guess that is this. So let's just read this out. What values for x locally maximize the value of f of x? So it looks like x equals 0 gives you a local maximum. That makes sense? Same idea, but minimum instead. Are there any inputs which look like they produce a local minimum? Yeah.
Wouldn't that be like the other tip of the W? So like, yeah, that's the second point.
Yeah, there. So what x value corresponds to that point?
That would be x equals -3.
Think so? Are there any other points where if you only look really, really close to them, you see something that looks like a local minimum? Yeah.
The other point that we talked about?
Yeah, it sure looks like this is a global maximum. But if you only look nearby, it also looks like a local minimum. So also, x equals 2. All right, so you know how to find them. You know what they mean. Let's just now write down the actual definitions. Let's write down some formal sounding mathematics for these notions. Yeah.
So does x equals 5 not count as a local maximum?
Yeah, so I won't want to count endpoints as local anything. Somehow, like, you can't even check. So the reasoning is, and this will make more sense when I write down a definition, like, I don't know what happens out here. Like, I can't tell what the function wants to do beyond that input. So I won't want to call it a local anything. Yeah, that's a good question. whatever definition I put out here, endpoints won't count. Groovy. All right, so let's write down some definitions. So what does it mean to be a global maximizer? What does it mean to be an input which maximizes a function? Well, that input should achieve an output that's like at least as big as every other output. So an input, C, is called a global maximizer for a function if for every other input x, f of C is at least as big as f of x. How do people feel about that definition? Yeah, and I think it works in terms of this example we just did. So it looks like in this example, C equals -5, the input is a global maximizer. And let's just see why. By looking at the graph, what is f of -5? What do you get when you plug in x equals -5? +5? Is every other output value of this function at most 5? Yeah, so it works. A function is called a global minimizer if for every other input x, f of C is at most as big as f of x. And input C is called a local maximizer if for every input x which is close to C, an input is a local maximizer if the same, but the inequality is opposite. Yeah.
What does it say after the -5 up there?
C equals -5. Oh, well, that's really badly written. That's supposed to be the one global maximizer. Yeah, thank you. Sometimes, it actually didn't look so bad when I looked at it on paper, but it projected really badly. That's a little bit on it, right? Yeah.
So like for the quiz tomorrow, so will this content be on the exact for the quiz tomorrow, or will you save that more for the exam?
I would regard it as fair. You should look at the sample, and the sample is designed to be fairly representative.
All right.
So what I think would be totally reasonable to do is to ask you, look at this graph, what's the biggest output value you see? That doesn't seem so onerous, I hope.
All right.
Cool. So I think I want to stop there on this topic, and let's begin on something else. So what we've been doing so far is studying like properties that you can read off from functions and graphs and how they relate to each other. During the next series of topics, what I'll start building is, well, what are some ways of understanding graphs of functions? So what we'll start with is, here are just some functions whose graphs you should know. We'll talk about the graphs, we'll draw them, they'll informalize them. And then we'll start thinking about, well, what happens when you like change the graphs? If you know the graph of the square root function, can you tell me what the graph of this function should look like? Square root of some stuff inside of the square root plus 7 with an extra negative sign. So that's the goal. So let's start with this. So let's pull up the graph of some power functions, things that look like x raised to a power. So I guess the first one is straightforward enough. What does the graph of y equals x look like? Should be like a straight line, right? It's a linear function. What's the slope of that line? 1? Good. What is the x-intercept of that line? Yeah, the 0, 0. Right, the intercept should be a point. But like, you knew the right answer. Cool. So there's the graph of y equals x. What does the graph of y equals x squared look like? Well, let's see. There will be some computer demos done today. There's a graph of y equals x. There's a computer-generated graph of y equals x squared. And let's see. Yeah, this will be fine. 1 squared is 1, 0 squared is 0, negative 1 squared is 1. And it opens up like this. Fair enough. Let's keep on going. Y equals x cubed. And that seems reasonable. It's negative sometimes, but negative cubes are negative, right? Negative 5 cubed is negative 125. Cool. And now maybe we'll go on just a little bit. Y equals x to the 4th. How would you describe this graph? What are some things you could say about it? I don't have a single answer in mind. Yeah.
Like, I would say it's similar to like y equals x squared, but instead you're doubling the power.
Yeah, it's visually similar to x squared. Maybe you see that, like, if you look close to 0, it looks like you've squished it down. But if you zoom out, it looks like you've stretched it up. Which makes sense, right? If you raise something to the 4th power, it's like bigger than it was before. But graphically, maybe we'll just, so I'll try to make it boxy or close to 0. It curves up. People feel pretty good? Let's try to ask some questions about these. So, take a look at those odd power functions, things that look like x to an odd power. Maybe I just don't want this pulled up. By the miracle of television, I've pulled up more of those. If you want to look at those graphs, they're graphs of functions. Are those functions even or odd or not odd? Even? Odd? Neither? Unclear. Okay, so let's remember, like, how do you check for evenness or oddness? Even was out, so like, no one even. So let's try to decide if it's odd. So a function is odd if you can reflect the function over the origin and get the same graph back. So let's focus on, I don't know, the green one. Make the rest of them disappear. So there's a point on the graph. Let's reflect it over the origin. Do I get a point on the graph? In fact, if I take any point on the graph and reflect it over the origin, do I get the same thing back? Do I get a point on the graph back? Yeah, that's what it means to be odd. So these functions are all odd. And maybe I'll give you another one which works well if you have like something drawn on paper. So reflecting over the origin is the same as rotating by 180 degrees about the origin. Let's check that. I will pin down the origin, take that graph, rotate it 180 degrees, except I can't in the space provided. Does that graph look the same as it was before I rotated? I think it does. So yeah, that function is indeed odd. In fact, all of them are odd. Let's pull all of those odd power functions up still. Whew, no. So if you were to look at these and I asked you where are the x and y intercepts of these functions, what would you tell me? 0, 0. It doesn't matter if I ask about x-intercept or y-intercept. For these functions, they're the same. Where are those functions decreasing? Are they ever decreasing? Nope. Where are those functions increasing? Everywhere, I think. If the inputs go left to right, the outputs are always going up. Nice. So there are some facts about odd power functions. Now let's pull up the even ones. So there are even power functions, x squared through x to the 8. Even or odd? Even? Odd? Neither? Unclear. Excellent. Yeah, they're all even. They all have symmetry over the y-axis. Where are the intercepts of these power functions? X-intercepts and y-intercepts. Yeah.
1, 1.
Ah, okay. The question was unclear, so what you answered was a totally reasonable interpretation of what is written. Those are definitely points where these graphs all intersect each other. And that's a good thing to know. That's a reasonable thing to know. Worth writing down. What I had intended to be asking about was where are the x and y intersects? So where do those things cross the x-axis? Yeah. Yeah, 0, 0. Maybe that's a better way of writing it. The x and y intercepts are at 0, 0. Are those functions ever decreasing? Where are they decreasing? Negative infinity to 0, right? If you look along these inputs, as the inputs go left to right, the y values go down. And so they are increasing the rest of the time. People feel pretty good? All right, so we have these functions whose graphs you should now just internalize. The graph of any even power function, they all look qualitatively like x squared. All the even power functions have really similar looking graphs. All of the odd power functions look qualitatively like x cubed. People buy that? That seem okay? So there are a bunch of elementary functions whose graphs you should just think of as being graphs you know. If you can build something out of those pieces, you can understand the graphs in terms of those pieces. So let's talk next about the root functions. So let's start by thinking about the square root function. You already somehow know what the square root function should look like, right? Square root of 0 is 0, so it should go through 0, 0. I can't plug in a negative, so I won't see any x values that are negative. Its graph should look something like that. Let's explore why the graph should look like that. So let's think of it this way. You see y equals the square root of x, square root of x. If you wanted to take that and solve that for x, what would you get? You would get x equals just say it louder.
Y squared.
Yeah, perfect. So that means that whatever this graph looks like should look like the graph of y equals x squared, but all the x's and y's are switched. If you think of y's as inputs and x's as outputs, you'll get the graph of x equals y squared, and so I know what that graph should look like. So here in red, I see x equals y squared. If you just saw the bit in red, would you say that that's even the graph of a function? Just the stuff, well, including this. If you saw this graph, would you say that's the graph of a function? No, it fails the vertical line test. And so here's the fact. Y equals root x is given by the positive y value with y squared equals x. So it looks like the graph of x squared, but reflected over, well, the x's and y values are flipped, and then you only look at the positive values on it. There's the graph of the square root function. Yeah.
Wait, what does it say over, so y equals the square root of x is given, this is given by, or?
Yes.
Okay.
So the rule that gives you the square root function is it's the positive choice of y whose square is the input. Which makes sense, right? The square root of 16 is 4, because 4 is the positive number whose square is 16? Yeah.
Oh, can you put the paper down a bit?
Yeah. Thank you.
Thank you.
I should also do this so I have more screen space. Nice. Cool. Of course, we can talk about other root functions. If you want the cube root function, well, let's think of it the same way. If you saw y equals cube root of x and solved that for x, you would get x equals y cubed. So the graph of the cube root function should look like the graph of the cubing function, but the x's and y's are switched. So instead of looking something like this, it looks something like that. And so that was just by thinking in terms of x equals y cubed. If you want to see that graph, would you say that is the graph of a function? Yeah, it passes the vertical line test. So that's it. There's the graph of the cube root function. If you want the fourth root function, do something similar. Take the fourthing function, raising to the fourth power function. Flip the job of x and y. You don't get a graph. You don't get the graph of a function. So you only take the positive values. If you want the graph of y equals x to the fifth, it'll look like the graph of y equals x to the fifth with the x and y values. People feel pretty okay? Yeah.
So for clarification, this all graphs like functions, they will all like pass the vertical line test, and all functions with even functions, they wouldn't pass like the vertical line test. So I guess it's like
So let me extract the second bit first. So you said if f is even, then I'm going to be like vague sounding. If I take an even function and I flip all the x and y values, then the result fails the vertical line test.
alright.
And the reason for that, so whatever an even function does, it has to do the exact same thing on the other side of the x-axis. Flip over the line y equals x. Well, flip the x and y values, you'll get a picture like that. It has to fail the vertical line test.
Okay.
The other thing you said, that odd functions will automatically pass, is not true. And let's see an example. So there's a function. Does that look odd? Yeah. It's not an odd power function, but it is an odd function.
Okay.
Here's what you get after you flip the x's and y's. Does that pass the logical line test? So just being an odd function isn't enough to guarantee. But every odd power function, everything that's like x to an odd power will.
Okay.
Yeah. Good observation. I like that. So let's read off some properties. So let's see. No, let's do odd first. Odd root. Even root. And you should have the graphs pictured in your mind, but let's also just pull up the picture. So let's see. Odd first. So here are some odd power functions. X to the 1/3, x to the 1/5. All right, so I don't know in Desmos how to type cube root, but a computer will understand a fractional power by doing that anyway. So there are some graphs. They're all odd root functions. If you were to look at those graphs, are those even or odd or not? Even? Are they odd? Neither? Unclear. Awesome. Yeah, they're all odd. Where are the x and y intercepts of those functions? So where are the x-intercepts of those functions? At the origin? Where are the y-intercepts? Yeah. Yeah, perfect. Where are those functions decreasing? Are they ever decreasing? So where are they increasing? Yeah. You meant the right thing, but I would never say the negative one after the positive one. Purely for orientation reasons, you should always think of things going from negative to positive. You can think of them the other way around, but you shouldn't. All right, the even root functions. But you meant the right thing. So there are some even root functions. Are those functions even? Folks for yes? Are they odd? Any folks for odd? Anyone for neither? Anyone for unclear? So, let's check something. So, being an even function should mean that if you take any of these functions and flip them over the y-axis, you should get the same function back. So if I take that red function and flip it over the y-axis, do I get the same function, the same graph again? No, I get like that graph. It is not even. So maybe I'll ask again, is it odd? Anyone who now thinks it's odd? Okay, good. Good, it's not odd. Its domain isn't big enough. Where are the x and y intercepts of this function? Where does it touch the x-axis or y-axis? Good. Yeah, right at this point. And you can even zoom in and see it closer. Where are these functions decreasing? Are they ever decreasing? Where are these functions increasing? Include or exclude 0. That seems reasonable. It's in the domain, so you can include it, and it certainly looks like it's increasing even if you include that at that endpoint. Nice. So there are a bunch of elementary functions. Maybe there's one last one that you already know, so let's just recap it. The absolute value function is given by absolute value of x equals x if x is bigger than 0, 0 if x equals 0, negative x if x is less than 0. And we've seen the graph, right? When x is bigger than 0, I should see y equals x. When x is less than 0, I should see y equals negative x. And there would be a gap at 0, but it's filled in by this statement that absolute value of 0 is 0. So let's read some things on. I guess there's one that's not lit in the list right now. Is this function even, odd, or neither? Even? Odd? Neither. Unclear? Let's think of it two different ways. So evenness means that the function doesn't care if you plug a negative in. Does absolute value care if you plug a negative number into it? No. It should give the same output value regardless of whether or not the input is negative. That's exactly what even should. So it should be even. If you look at that graph and flip it over the y-axis, do you get the same graph back? Yeah, I mean, I guess it's confusing because I've like color-coded it, and like the two colored sides will switch. But that's fine. The colors are efficient. So this thing is even. What is its domain? What inputs can you plug into the absolute value? Yeah.
Can the domain just be like anything, like negative infinity, infinity, such that before it doesn't really matter what number you put in?
Yeah, you can plug anything in. Alternately, if you continue that graph on, do you see absolutely every x value on that graph? Yeah, cool. What's the range? What y values do you see on that graph? Yeah.
0 to infinity.
0 to infinity. Should I include or exclude 0? Include. Where is this function increasing? Yeah. 0 to infinity. Including or excluding 0? I'd want to, but I'm not going to be picky about that. So, where is it decreasing? I guess the rest of the time. Where are the x and y intercepts of this function?
0, 0.
Yeah. So all of the intercepts of these elementary functions are all 0, 0. And somehow, like, if you have a function that's like elementary in some sense, that just should be the case. Otherwise, you should just like translate it to get the intercept there. Cool. People feel good right now? So I want to start in on one more thing. And this is the idea of transformations of functions. So here's the statement. Suppose you know what the graph of y equals f of x looks like. Then you can get the graph of y equals f of x plus c, y equals f of x minus c, y equals f of x plus f of x plus c, y equals f of x minus c by just shifting. You can get the graph of y equals f of x plus c by shifting up by c. So you can get the graph of f of x minus c by shifting down by c. Graph of f of x plus c by shifting left by c. Graph of f of x minus c by shifting right by c. So there's just a statement. And let's see, the stuff with the inputs, when you replace x by x plus c, that's like the opposite of what you might expect. And that is actually correct. But in order to see it's correct, let's at least check it for an example. So let's try to use these instructions to get the graph of x plus 2 squared and x squared plus 2. So let's try to graph those by hand by using these tricks. So first of all, do we just already know what the graph of y equals x squared looks like? Yeah, it looks something like this. So, according to the instructions above, what should I do to that to get the graph of x plus 2 squared? I should shift it in which direction? Left, by, awesome. So this vortex, to use the fancy word at 0, 0, will go left by 2. It'll look something like this. And how would you shift to get the graph of x squared plus 2?
Up to.
Great. And just in order to verify that this is actually correct, do you think we could now have a computer graph these things by plugging in a bunch of points? Yeah. You could do it using a handheld graphing machine. Desmos looks better. So there's the graph of x plus 2 squared. Does that agree with what we just graphed? I guess there's the graph of x squared, but we already knew that. And there's x plus 2 squared. Nice. So there's the idea that this section is building. So one thing you can do is if you have these two moves, you know what happens when you change the input, you know what happens when you change the output. What happens when you change the input and the output? Let's suppose I wanted you to sketch the graph of the square root of x minus 2 plus 1. Well, I know what the minus 2 does, and I know what the plus 1 does. Let's just do each of them one at a time. And let's, I don't know, choose an order. Well, let's start with square root. What does the graph, you know what the graph of the square root looks like. So let's start by just drawing that. Start with the graph of y equals f of x. So that's y equals the square root of x. Looks something like that. And so let's deal with just one of the ingredients at a time. If I wanted the graph of y equals x minus 2 squared, how does the graph change to get that new function? How does that change the graph? Yeah.
It goes to the right too.
Right by 2? So this endpoint is now here. Everything is shifted to right by 2. And I guess we just have to deal with this plus 1. So that's the minus 2 dealt with. What does that plus 1 do to the graph? Up 1. So this point at 2, 0 is now up here at 2, 1. Graph looks something like that. People feel pretty okay? There's nothing so fancy about these ideas, I don't think. But these increase the set of functions whose graphs you know by quite a bit. Yeah. So I think I'm going to forego this next example in favor of hitting one new notion. So let's think about what negative signs do. And they'll do something that's not terribly surprising. So maybe I'll speak in just a little bit. If you want to graph this negative f of x, well, that says you want like to take all of the output values, so all the function values, all the f of x's, and make them negative. Like all the y values on the graph, you want to become negative what they used to be. So let's write that down. I'll write this down two ways. Get the graph of negative f of x by multiplying all y values by negative 1. Or, another way of saying that same thing, right, that's the same thing as taking points in the plane and flipping them over the x-axis. So just two different ways of saying the same thing. Or if you want the graph of f of negative x, you will multiply all x values on the graph by negative 1, or, if you prefer, flip over the y-axis. And let's just see that done for one example. So here is the graph of x cubed minus x plus 1. There it is. So if you wanted to get the graph of negative f of x, how would you transform the graph of this function? What do you need to do to it? What axis should you flip it over? Yeah.
Or no,
Yeah. So that's like the subtlety. If you want to say like which it flips over, if you're like too quick, you'll get it exactly wrong, even though you mean the right thing. Do the flip that changes y coordinates. So this point is already on the x-axis, so it'll stay put. The y value is 0, so making the y value negative doesn't do anything. Here the y values get negative, so they'll get positive instead. Go up, down. That has now been flipped over the x-axis. If I want the graph of f of negative x, I should take that exact same graph and flip it over the y-axis this time. So this x-intercept that's negative 1 and some change will now be positive 1 and some change. These y values getting 0 will still get 0, but now the x values will be positive. Nice. And maybe I'll close with just one question and an observation. So these two functions, one f of negative x, one negative f of x, are those two graphs the exact same? And what would be x? Good, they look pretty similar. It looks like one of them is the other is like shifted vertically. So there's a relationship between them, but they're not equal. So here's an observation. It sure looks like f of negative x is not the exact same thing as negative f of x. And out of that sense, that false equality that's involved, what thing can you say about the original function f? Is it wrong? No, it's specifically not odd. So this function is not odd, which you already knew, but it's worth seeing in a different way from looking at a graph. Neato. So, I'm at time. I'm happy with where I am progress-wise now. I'll see you tomorrow for that quiz.